So now we will do the proof of one part of the Karamata representation theorem. We will show that if I have a function that can be written up on this form, then that function is a slowly varying function in the sense that it satisfies the definition for a slowly varying function. Let's just recall the assumptions that we place upon this function. We assume that it can be written in this way with a C0 of x that tends towards a positive constant C0 as x goes towards infinity. And also the epsilon of t that is inside the integral here goes towards 0 as t goes to infinity. So let's just get started and take this representation of L and plug it into this ratio and see if we can make that ratio go to 1. So let's start by saying fix C greater than 0. Then L of Cx over L of x is equal to, well, we have C0 of Cx multiplied by the exponential of the integral from x0 to cx, and I have epsilon of t over t dt, and then we divide by c0 of x, and down here I have the exponential from x0 to x, and epsilon of t over t dt, right? Okay, so the first thing that we can notice is, well, among other things, is that C0 of Cx goes towards a positive constant C0 as x goes to infinity. The same is true for C of x. It goes towards the same constant. So their ratio must necessarily go towards C0 over C0, which is equal to 1. This means that the first term in this product, this thing here, this tends to 1 as x goes to infinity. And since we want to show that the entire ratio goes to 1, it suffices to show that this part goes to 1. Question mark? So let's just call this thing star of x and try to write it up where we gather the terms with the exp. So star of x is equal to the exponential of this thing minus this thing, right? So we want to take the integral from x0 to cx and subtract the integral from x0 to x. Now there may be a vague point of confusion here because we have x0 here, we have x here, and let's just say cx is here. And what we then do is we take the integral of some function from x0 to cx, and we remove the part that goes from x0 to x. So what we're left with is with the integral from x to cx. However, this is based on the assumption that cx is greater than x, right? I mean, if it was the other way around, then we would have the integral from cx to x, or something like that. So the thing here is, in order to make this drawing, we need cx to be greater than x. And hence, I mean, if cx is smaller than x, we could also still rewrite this into x to cx, but then we would just have to remember that this number up here is smaller than this number down here, and remember that this integral always evaluates to an opposite sign, and that's just kind of messy. So let's just assume for the time being that c is greater than 1, and that will allow Cx to be greater than x. And what we then want to show is that this expression here goes towards 1. And we notice that for the exponential of this thing to go towards 1, it suffices to show that the integral inside tends to 0 as x tends to infinity. Now, what do we recall about epsilon? From our assumptions earlier, we recall that epsilon is a function that goes towards 0 as t goes to infinity. In this statement here, we want to show something about the integral of epsilon. The problem that we kind of have is epsilon of t in itself is kind of nasty because we don't know how to integrate a function that we don't know, and we don't know the expression for epsilon of t. So one thing we'll have to do is we kind of have to try to get rid of epsilon of t. We want to try and see if we can turn this epsilon of t into something else that's more manageable. And as I just mentioned, we will try to recall that epsilon tends towards 0 as t goes to infinity. And for that, we can make a drawing of what happens. So if this is the graph for epsilon of t, for epsilon, so here, then we can try to draw two delta bands. Let's just say the delta bands go like this. So for some value delta, we make a band that's delta thick in both the positive and the negative direction. And then because epsilon of t goes towards 0, then we know that there will be some time point, which in the literature we can call t0, which there will be some time point t0 for which after that time point epsilon of t will always be bounded between minus delta and delta. Now that is kind of nice because, well, let's just try to write this up rigorously. For any delta greater than 0, we can find a t0 such that for all values t that exceed t0, epsilon of t, and note that I use numerical values because epsilon can go both up and down, and whatever. So the numerical value of epsilon of t goes towards, for all t that are greater than equal to t0, the numerical value will be bounded by delta. Now, what does this mean? This means in particular that, well, I'm letting x go to infinity, right? So I will be evaluating this integral further and further out. And especially if we go so far out that x lies after t0, then when I evaluate the integral of epsilon of t, then the size of that integral will be bounded by, in particular, the size of this box here. I mean, in a second when we evaluate this, we will evaluate the numerical value. So we're going to take this, add with this, and this area is going to be certainly bounded by the box that has height delta and has length x to cx. So that's very nice. And we will also write this up mathematically. So we can write, so for x greater than t0, we have that the numerical value of this integral. So we want to show that the numerical value of this integral can become arbitrarily small. So we want to show that it can be bounded by something that has to do with delta and something that has nothing to do with x. So the first thing we can do is move the numerical value inside and pay for that with an inequality. And now we can use that epsilon of t is numerically bounded by delta to write up another inequality and remove the epsilon of t and write delta. And this is very, very nice and comfortable because now we have removed the thing that we deemed nasty. And this allows us, since delta is a constant, to just evaluate the integral of 1 over t. And the antiderivative of that is log of t. So I will take log of cx minus log of x, which is log of this ratio. And this is equal to delta multiplied by log of c. And we can see that this expression does not depend on x. Depend on x. And also that delta was arbitrary. So we have shown that the integral here does in fact go to 0 as x goes to infinity. Now one might say, well, when we were up here, when we wanted to say that this integral went to 0, already at this point, we could have just waved our hands and finished. And in a sense, that is also kind of true because you can see that epsilon goes to 0 and you go further and further out and you think, well, it won't really hurt anybody. So maybe this entire integral just goes to 0 because epsilon goes to 0. But the thing is that this kind of hand waving can sometimes be a little bit dangerous if you do not notice the right things. So the thing that you have to notice is this. The further out we go, the bigger the x becomes. The bigger the x becomes, the bigger the difference between cx and x becomes. And thus we will be integrating epsilon of t over a bigger and bigger interval, even though epsilon becomes smaller and smaller. So the question is this: how come the integrand wins over the length of the integral? And the reason why it does so is because we divide by t, which is in a sense the length of the integral to some respect. So the reason why this entire thing doesn't just blow up as the interval length blows up is because we divide by t. If we had not divided by t, this entire thing would not work. And that was also kind of what we concluded in the proof when we took the integral of 1 over t. Because if we did not have that, then inside here it would just be a 1, in which case, well, if we just had a 1 inside here, then it would be cx minus x. Yes, and then it would not work because we needed the cx and the x to cancel out the x by dividing them. So this divide by t is crucial to make things work. And that's a very nice and comfortable point. Just to finish off this exercise, recall that we did assume that c has to be greater than 1. However, you can just repeat the entire thing with c smaller than 1. So that's not really a big problem. You can also construct some argument where you say, well, now we just showed that what we just showed was that L of cx divided by L of x does in fact go to 1 as x goes to infinity. And then we can say, well, we showed that for c greater than 1. If c is smaller than 1, then we will be looking at L of cx divided by L of x. But we can also just call that L of y divided by L of C inverse y, where we let y be equal to Cx. And then that will go towards 1 since C inverse is greater than 1. And we have already shown that this ratio for a constant that's greater than 1 goes towards 1. So you can get around the C greater than 1 assumption in multiple different ways. Yes, so that was the proof of A. See you in the next video where we will do exercise 6B.